Now, question number 21. The mean intensity of radiation on the surface of the sun is about 10 to the power 8 watt per meter square. The RMS value of the corresponding magnetic field is closest to. So this is intensity, and the formula of intensity from the chapter electromagnetic waves, or formula of the average intensity, is given by half epsilon naught E naught square into C in terms of the electric field. In terms of magnetic field, this formula becomes B naught square by 2 mu naught. So we have to use this relation. We have to find the RMS value. RMS value B RMS, since साइनसोइडल वेरिएशन होता है इनका, तो इसलिए बी आर एम एस जिस तरीके से अल्टरनेटिव करंट के लिए होता है उस तरीके से यहाँ पर भी हो जाएगा. इट विल बी बी नॉट बाई रूट 2. So basically this b naught square by 2, we can further write it as I is equal to, this b naught square by 2 is b RMS square by mu naught, and this b RMS will be given by under root mean intensity by mu naught. Now just putting the values. So this I is given as 10 to the power 8, and this mu naught is 4 pi into 10 to the power minus 7. On solving this, the answer is approximately 6.47 into 10 to the power minus 4. But we have to just select the order, and the order is 10 to the power minus 4 Tesla. So the correct choice is option number 2. Question number 22. A resonance tube is old and has jagged end. That means there is some end correction. It is still used in the laboratory to determine velocity of sound in air. A tuning fork of frequency this much hertz produces first resonance when the tube is filled with water to a mark 11 cm below a reference mark near the open end of the tube. The experiment is repeated and another fork of frequency 256 Hz which produces first resonance when water reaches a mark 27 cm below the reference mark. The velocity of sound in air obtained in the experiment is close to. So the question number 22. For open organ pipe or open tube, the fundamental frequency, this length is L of the pipe, and if there is some end correction, then effective length will become L plus E. This L plus E is lambda by 4. Lambda is 4 times L plus E, and frequency is given by V by lambda and V upon 4 L plus E. We have to use this relation for both the cases given in the problem. In the first case, from open end, the water level is this much, 11 cm, and let's say E is the end correction. So in the first case, 512 is equal to V divided by 4 times 11 plus E. This is equation number 1. In the second case, water level is somewhere down here. This is end correction. End correction will remain the same, and now this length becomes 27 cm. So from open end it is 27, and the frequency is now 256 Hz. So it is 256 V divided by 4 27 plus E. So these are the two equations. From these two equations we can solve, and after solving we get V is approximately 327.68 meter per second, and the closest choice will be, obviously it is 328 meter per second, option number 1. Question number 23. An ideal gas is enclosed in cylinder at pressure of 2 atmosphere and temperature 300 Kelvin. The mean time between two successive collision is 6 into 10 to the power minus 8. If the pressure is doubled and temperature is increased to 500 Kelvin, the mean time between the two successive collisions will be. So this is the question from KTG, kinetic theory of gases. And from the chapter, you should know that the time between two successive collisions or relaxation time is given by the formula kT divided by root 2 pi sigma square velocity into pressure. Sigma here represents the size of the molecules, diameter of the molecules, K is Boltzmann's constant, T is temperature, P is pressure, V is velocity. So these factors are not going to change. Boltzmann constant is not going to change. Temperature and pressure is changing, and this velocity. So we know that all the formulas of velocity, whether it is average, RMS, in all the formulas V is proportional to square root of the temperature. So there will be a temperature term in this velocity. This is square root of T. So T upon square root of T, we can write this time is directly proportional to root T divided by pressure. So this factor, using this factor, we can determine the relaxation time at 500 Kelvin. So relaxation time at 500 or relaxation time in final situation divided by initial situation, this is given by T2 by T1 under root, and for pressure it will be inverse P1 by P2. Just plug in the values. Initially it is 6 into 10 to the power minus 8. The temperature T2 is 500 Kelvin. Initially it was 300 Kelvin. Pressure is doubled. P1 was 2 and now it is 4. On calculation, it is approximately 3.87 into 10 to the power minus 8 seconds. And the closest choice from the options is option number 1, 4 into 10 to the power minus 8 second.